Hello, and welcome to this seminar from Micro-Epsilon. Today's presentation is all about thickness measurement and the challenges you might face in making reliable measurements. My name is Glenn Wedgbrow, and I am the Business Development Manager for Micro-Epsilon here in the UK. I'll start by giving a short introduction to the company Micro-Epsilon, before posing the question, why measure thickness? And from that, we will explore the challenges to making reliable thickness measurement. I mean, thickness measurement is easy, right? What could possibly go wrong? I'll follow up the challenges posed with solutions and applications and show you where our systems have been used. So who or what is Micro-Epsilon? For the benefit of those watching for the first time, Micro-Epsilon are a German company established in 1968, originally selling American high-precision strain gauges, which is actually where the name Micro-Epsilon comes from. Around 1980, we developed our first eddy current sensing technology and then moved away from selling strain gauges and started to develop our products for displacement measurement. From just 2 people, the company has grown to over 1,200 employees worldwide. The entire product range is developed and manufactured within the Micro-Epsilon group of companies, of which Micro-Epsilon UK is one. The organisation has been built by engineers, and combined we have more than 5,000 years of collective technical knowledge across multiple industrial sectors. One of the keys to our success is that we treat our customers as partners, working with them to ensure stable, long-term relationships worldwide. Our current product offering falls into 3 basic categories: measurement of displacement, measurement of temperature, and inspection and measurement of colour. Across these 3 fields, we've developed and utilised technologies that allow us to measure positional changes from as small as 30 picometers and distances up to 3 kilometers. With our infrared temperature sensors, we can measure from -50 degrees C to +3000 degrees C, and for colour, we can detect changes or shades much finer than a normal human being. We're able to offer products as catalogue one-offs to fully customised solutions in hundreds or thousands of units. Indeed, our production capability is more than 1 million products a year. So why do we want to measure thickness? There are many reasons that thickness is important. All materials have a tolerance in production. Materials produced too thin or too thick could cause a problem further down the line, or perhaps at your end customer's site. Maybe they use this material and build it into a system that then fails or doesn't fit. Changes in thickness during production can indicate wear of components, for example in extrusion dies or on rolling stands. Monitoring trends can point to early warning signs. The traditional method of checking thickness is often to take a measurement sample from the start of the production run and then again at the end. But what happened in the middle? Of course, if you find it out of tolerance, that's a lot of scrap to consider. So you might choose to take more readings during the process. If that check is done manually, then that often requires the production line to stop. And anyone will tell you that most process variability will come in the start and stop phases. So keeping a line running is generally key to getting things consistent. Ultimately, checking the product thickness as it is produced ensures that the end customer receives the quality of product expected. Perhaps the most simplest thickness measurement is the single-sided measurement against a reference or datum surface. It seems straightforward. First, you zero or tear the sensor on the datum surface, and then insert the target to be measured. The reading of the sensor is changed or displaced by the material thickness. However, there are a number of uncertainties with this method. If the reference or datum moves after mastering, then the reading will be incorrect. Similarly, if the target does not sit correctly on the datum surface, then the air gap is also included in the measurement. The same issue can also occur with tilted targets. If we are only allowed to view a target from one side, then we have to consider if we can combine technologies to enable accurate measurements. Where we have a mix of different material types, we can utilize those different material properties to our advantage. For example, an eddy current sensor in combination with one of our laser triangulation sensors is used to measure sprayed skin thickness. The eddy current sensor measures the distance to the nickel-coated spray mold, which is distance A, and has an opening in the center through which the laser sensor measures the distance to the sprayed part, distance B. Eddy current sensors only measure against metallic targets, and therefore see straight through the non-metallic spray coating. The use of the air coil in our eddy current sensors makes this combination possible, as the laser sensor can look through the eddy current sensor at the same measuring point. When both signals are subtracted, the thickness of the applied sprayed skin is measured, which is marked as C. Or another well-used sensor combination is done with our eddy current and capacitive sensors for non-metallic materials passing over a roller. Movement of the metal roller is considered by the eddy current sensor, and the capacitive sensor measures the material or coating thickness. If your target is transparent, then you have the possibility to make a relative measurement of the material thickness from one side, using one sensor with our interferometer or confocal technology. The use of light refraction creates edges or return signals that indicate the transition between the air and the material. Knowing the refractive index of a material will enable you to accurately measure the material thickness, provided it stays within the measurement or work. Of course, if single-sided measurement is not suitable or the challenges cannot be overcome, then in many cases customers will want to know the true material thickness by measuring the material in free space, which requires having space on both sides of the material so that a measurement can be taken from both surfaces. When you consider this setup, then there are a number of challenges that must be considered and either overcome or accepted. The first challenge is sensor alignment. Seems fairly obvious. Sensors must be positioned so that the measuring spots coincide through the full measuring range of the sensor. There should be no offset, tilt or inclination of the sensors in relation to the measurement object. For example, with a sensor offset of 1 mm and inclination of 2 degrees, the effective error equals 35 micron. And at 10 mm target thickness, this error increases to Particularly with laser triangulation sensors, you should also take note of the beam spot location relative to the sensor housing. You should not necessarily assume that two apparently identical sensors will position the spot in the same place. Standard sensor housings are not usually precise enough for precision thickness measurement unless time is taken to align them correctly. For example, here there is a 160 micron variation in position of the spot from housing to housing. To aid customers making their own thickness setups, the new ILD 1900 laser triangulation sensor uses an innovative sleeve mounting arrangement to tighten the spot spacing from housing to housing. So here the spread is less than 20 micron from one sensor to When you have two sensors looking at the same target, you must consider that each sensor has its own cycle time. If your target is vibrating or moving in the gap between the sensors, then it's very easy to introduce an error. Consider a target oscillating up and down by 1 mm at 20 Hz, 20 times a second. A difference in capture time of just 1 millisecond between your sensors would equate to an error of 125. Our next challenge is the relative position of the sensors and their measurement ranges. Depending on how the sensors are arranged, the position of the target edges must stay within the measuring field. If your sensors are set so that the measuring zones do not overlap, then situations can arise where one sensor may not see the target, which is indicated by the red box, that is not seen by the lower sensor. Additional consideration should be given to process start and stop conditions. Is the material held in tension at all times? Speed changes in the line can induce upward or downward movement. Is the setup able to capture these events if needed? Ideally, make sure sensor ranges overlap and cover the full range of material movement, or at least the accuracy of a sensor is often referred to as its linearity. The linearity value each measurement sensor has its own measurement uncertainty or non-linearity. This means that at any given point in the measurement range, the actual reading from a sensor can vary by a percentage of its measurement range. So taking just two sensors without any additional processing means you need to consider both sensors' uncertainties with respect to the accuracy you are looking to. For example, without adjustment, just moving a target 200 micron up or down can result in errors of 8 micron. The position in the range also has potential to affect the true value. To get around this, you must calibrate. Even when we have aligned the sensors, synchronized them, etc., there is still a further challenge that can affect everything: thermal changes. When measuring a target thickness in free space, the gap between the sensor and the opposite sensor is critical, as this is the constant on which the differential measurement is based. Taking a mechanical frame with a pair of sensors and cycling the temperature shows that the effective change with just a 5-degree swing is up to 20 micron. In the chart shown here, we can see that as the temperature increases from ambient to plus 45 degrees, the relative thickness measured varies by up to 400 micron without any compensation. Your final challenge, if you've overcome the previous ones or accepted the errors associated, is to prove the capability. Exactly how do you check or confirm the performance of your solution? There will be two factors to consider here: the system repeatability, how much variability in the measurement system is caused by the measurement device, and reproducibility, how much variability is caused by different. So how can we look to overcome the challenges I have presented? Certainly we have to take each application on its own and assess the needs of the customer and consider the tolerances required and whether sensors alone are able to solve the task. But did you know that Micro-Epsilon has a systems division? Our systems division is focused on thickness and width gauging solutions for strip processing materials, including metals, plastics and rubber. All our key competencies can be found within the systems division. We use the measurement sensor technologies from within the Micro-Epsilon group. We develop our own software and algorithms, including all the automation, linear guiding, traversing and programming of robots. Most important is that we understand the mechanics of the systems we build. Our knowledge of the surrounding environmental influences such as temperature and how to overcome them is critical to the success and continued operation of our systems. And we now have more than 500. So how do our systems solve the challenges discussed? Alignment and synchronization are taken care of when purchasing a system from Micro-Epsilon. Knowing the overall gap or distance between the two sensors allows the calculation of thickness to be made. To establish this value, we first need to calibrate the system. A certified gauge block is positioned in the measuring path. This known thickness, combined with the readings from our sensors above and below the target, equal the overall measurement gap, dA. Our systems will periodically return to the calibration position to check for changes and readjust values accordingly. Once the gap is confirmed and stored, the system can then be moved onto the target to be measured. The thickness of the material will now be the known gap, dA, minus the sum of the individual measurements from the upper and lower sensor. A typical application is shown here with a traversing C-frame measuring strip metal thickness for crown, wedge and edge drop on a decoiling line prior to slitting. Calibration checks against the certified gauge block are performed at regular intervals to avoid inaccuracies that may be caused by changes in. I highlighted earlier that each individual sensor has its own measurement accuracy, and therefore, in order to get the best performance for the system, we need to understand the measurement behavior of the individual sensors and combine them. This is achieved in the systems department through use of a known target and highly precise reference gauge, which is moved through the measurement. The values of the sensors are recorded and the combined readings stored into a new linearization algorithm, which is used by the system software to calculate the true thickness reading. This is the extra step needed to achieve the total system accuracy, which is often better than the quoted individual sensor performance. Thermal compensation in an O-frame system works slightly differently. As we've already seen, the gap between the sensors is key to accurate thickness measurement. Even in an O-frame configuration, the mounting frame can expand and contract with temperature changes. Typically, the upper frame will move further than the lower frame. Heat rises, so the reference for the gap between the sensors can vary differently. The consequence being that the system reports a thickness change even though the real thickness. Micro-Epsilon O-frame systems use a patented compensation frame made from an invar material and is designed so that thermal expansion of the frame is transferred in the horizontal direction rather than vertically. But this is only part of the solution. The second element is to then measure the gap change between the main frame, which holds the sensors, and this invar frame. This is achieved through using two micro-epsilon capacitive sensors, themselves extremely accurate. Now, when the main frame expands or contracts, we can measure this change on the gap between both the top and bottom frame and compensate the effect into the thickness calculation. Even when the sensors are traversed across the full opening, the changing gap is continuously monitored and adjusted. As with the C-frame, we also have a certified gauge block included that can be positioned into the measurement zone. As we saw earlier, the chart shows the effective temperature change with no compensation employed. A 25-degree change in temperature is perceived as almost 400 micron change in thickness. The red line on the graph shows the real effectiveness of the patented compensation frame, which exhibits stable results even with the adverse temperature changes. Three optical sensor technologies are available for integration into the measurement systems. Single-point laser triangulation sensors offer a relatively low-cost entry into full thickness measurement capability. Confocal chromatic sensors provide the highest precision available, especially on shiny surfaces, whilst the laser line technology is the most commonly used for its excellent combination of high precision and one of the main reasons for the use of laser line profile sensors is that we are able to make a best fit line of multiple points taken from the surface. Even if some points are missing due to surface oils or textures, then the average reading is still good and valid. The application shown here is for quality assurance in China. The plates are 4.6 meters wide. We measure thickness, profile and width. In addition, a laser Doppler sensor is used for calculation of length and can be used to tie the corresponding thickness values to that specific position on the strip. Another consideration in the use of the laser line sensors is that the laser line can compensate for tilts in the material. If single point measurement is used, then there can be significant errors introduced by the fact that the measurement is no longer taken perpendicular to the surface. The line sensor allows for detection of the angle of the tilt and thus compensates to ensure the correct thickness value is measured. In addition, the laser line power or exposure time can also be adjusted to cope with oil films, emulsion and scale on the surface. It also offers the ability to measure profiled surfaces for both minimum and maximum thicknesses, which can be helpful in understanding the performance and wear of an embossing roller like on this checkered foot plate. A single point sensor. The more traditional method of thickness measurement in the metals industry has been the use of isotopic or X-ray gauges, but these can have limitations when it comes to handling, ongoing support and operation. As we use optical measurement techniques, we're generally not restricted on the material type we can measure. Our measurements are made against a certified gauge block and we do not have to recalibrate for different material types. Isotopic or X-ray need to know the material type being measured due to material property changes that influence the system's measurement behavior. As well as the fact that we have no radioactive substance to handle or control, there is no need for a safety area around the system other than normal guarding, and the fact we are measuring against a known target for calibration allows for the customer to perform their own capability checks and at any time to verify the system performance without influence from the supplier. Each measurement system from Micro-Epsilon comes with fully capable software for operation, data capture and analysis of the required measurements. The multi-touch functionality provides a familiar user experience similar to many smartphones and touchscreens in everyday use. The software also includes the means to check your system's capability at a touch of a button, performing both reproducibility and repeatability checks whenever required and without supervision from Micro-Epsilon. If you want to measure thickness, then we have three methodologies you can work with. Thickness sensor is a caliper-based solution with no traverse, just a reach of 200 or 400 millimeters with our single point laser triangulation sensors. No capability check, but it can be calibrated. Thickness gauge is a fully turnkey system for light industrial environments with traversing up to 400 millimeters and includes the software for capture and control. Thickness control is the option for heavy industry and greater spans or widths. We are supplying two different mechanical frames, O frame and C frame, which are further split into three series. Our entry-level systems are the new thickness gauge series for operation in non-critical ambient conditions, example processes that typically run without elevated temperatures. The most common systems we sell are from the 8200 series for processing lines and cold applications, plus aluminium hot rolling, as the heat radiated from aluminium is minimal. And our high-end systems are the 9200 series for high temperature environments. Our C-frame systems are provided on traversing rails. With this they can measure at any position within its reach or just the edge or centre as a fixed track. They can traverse back and forth across the whole width or make a combination of traverse, edge and centre line as required. Important to note is that the space needed beside the line is significant, especially for longer traversing systems. O-frames are able to do centerline, traversing or mixed combinations similar to C-frames. However, because the measurement is contained within the system, the overall footprint of the O-frame is much smaller than that of the C-frame systems. In hot mills, apart from the obvious challenge of environment temperature, we must also consider the ability of the measurement technology to measure the surface. Pointing a red laser at a hot glowing surface will saturate the sensor receiver, effectively blinding it and stopping it from being able to measure. However, this can be overcome by using a shorter wavelength sensor. Micro-Epsilon holds a patent for use of blue lasers to measure on hot glowing surfaces. Using the 405 nanometer wavelength allows readings to be taken on glowing surfaces with temperatures up to 1600 degrees C. The introduction of this technology opens the market for thickness measurements in hot mills. So we have the sensor technology capable of measuring the target, but how do we protect it from the harsh environment? The solution is a C-frame within a C-frame. A heat exchanger is controlled by a chiller with water flowing through it. Fans blow cool air through the inner frame and over the sensor, and then returns through the outer frame back to the heat exchanger. This flow ensures that the sensors and traversing unit are kept within the permitted operating temperatures and can be used to measure on plates with temperatures up to 1200 degrees C. So having seen the system technology, now let's take a look at some of the applications that have already been used in. Our first application is for monitoring the calendered rubber in a UK production facility. This O-frame system is used to monitor the profile of the rubber as various components and layers are brought together before being formed into the final product. Here we have a single-sided scenario measuring rubber on a roller. There is the combination of the laser point sensor and eddy current sensor to provide reference to the roller position. Another UK application utilises a combination method which is used for thinner materials passing over a roller, whereby a through-beam micrometer and eddy current sensor system combine to measure the material thickness. For this application, we're using C-frames to traverse across the coated metal. There are actually two systems utilised here, where we measure the base material before coating and then the overall thickness after coating. A subtraction of the before and after gives the painted coating thickness. Here we see the confocal C-frame measuring a copper strip. Note how shiny and reflective the surface is. This is no problem for the measurement with confocal technology. For this customer, the copper is used for electrical cabling, and the key parameter for the customer here is the frequency of the thickness deviation along the center line of the material. And we use a fast Fourier transform in the controller to output the desired value to the customer. Here we have a customized system installation which incorporates the main thickness sensors and in addition 3 of our optical micrometer systems which are utilized to measure the edge camber or straightness along the strip length. For this measurement, the line is stopped, and after we measure the thickness profile, the optical micrometers measure the edge position of the strip at 3 places. It should be a 1 meter separation between the first and last micrometer, but to save space, the information of the distance is 0.5 meters, and the straightness is extrapolated from the known measurements between these 3 positions. Using our blue laser technology, this C-frame is equipped with the cooling system to keep both sensors and frame cool whilst the measurement is performed. Here the material temperature is around 900 degrees C during measurement. Additionally, integrated into the system are infrared temperature sensors to provide product temperature in addition to the thickness profile. This system is installed at SMS Group, which our system manager describes as the mother of all C-frames. In particular, we increase the gap to measure up to 460mm thick plates. This is something that simply cannot be done using X-ray or isotope systems. Also, the environment is particularly challenging with plate temperatures up to 1240 degrees C. But in reality, the plates do not stay very long in the measurement gap, maybe 10 or 15 seconds, as the longer they sit stationary, the more the heat dissipates, and this can then affect the material properties. One of the emerging markets currently is that of battery production. In this industry, the requirements for accuracy are amongst the very highest, with requirements for system performance to less than 1 micron. Overcoming the challenges and taking care for the complete system allows us to meet and exceed the expectations of this industry. Here you see the very latest development, which is our thickness gauge O-frame systems, which is using the combination sensor to measure the coating thickness on the substrate. Also available for the systems portfolio is a comprehensive support package which can be tailored to each customer's requirements and ensures longevity and availability of the systems. As already mentioned, we have over 500 system installations around the world. Here are just a few of our satisfied customers. So, through this seminar, we've considered and shown our solutions or recommendations for solving these challenges to thickness measurement. If you have a thickness measurement challenge, then we have, at Micro-Epsilon, sensors and systems that can surely help you. You can keep updated on all things Micro-Epsilon through LinkedIn, so make sure you're following us, and also make sure you subscribe to our UK newsletter for product news and information about our next events and exhibitions. So that concludes my presentation. If you have questions relating to the content, then please email us at info@micro-epsilon.co.uk. Thank you for watching.